Our next topic is called quadratic forms. It's kind of following the whole idea of studying symmetric matrices. And this is a quick application of a symmetric matrix is to deal with quadratic forms. And then we'll see if we can hook this up to Calc 3 for those people that have taken Calc 3. There's some interesting theory about optimizing functions in a certain level here that's closely related to Calc 3. We did some sort of optimization already, kind of right, like the least squares lines and stuff. Anyways, if we get to it towards the end, we'll see some a linear algebra explanation of an interesting Calc 3 theorem or whatever you call it. Quadratic forms. So a quadratic form is a function that they'll call it Q that takes in an R vector or an N vector, I mean, and then it results in a scalar, and it can be computed by the expression the transpose of that vector times A times the original vector. And then for this to work out, we need A to be a symmetric matrix. A is called the matrix of the quadratic form. I need to adjust my page sizes. All right, so X, by the way, is like an arbitrary or a variable vector. We can call it XY, XYZ, or X1, X2, X3, or whatever. And we'll see it in a few different ways. So let's take a look at this first example and see if we can write what the quadratic form might look like. What do you think of when you think of quadratic? The quadratic formula. What else? Polynomial? I don't know. All right. Q is a function that results in a scalar. So in terms of, that's a good question, Lale. When we take a look at functions, we take a look at a function by looking at its domain, where its inputs come from, and then we take a look at its range, or where it outputs goes to, where its outputs go to. And so formally, the Q function goes from Rn to R. So in Calc 3, we can think about this as a multivariable function that results in a scalar. All right, so here A is a 3 by 3 matrix, so we're going to take a look at vectors in R3, and generically our X vector would be X1, X2, X3, or one can say that your X vector can be XYZ, which we might go into just so we can take a look at graphs of things. But for now, let's just say it's X1, X2, X3 is a vector. And so if we perform this calculation for the Q, we want the transpose of this column vector, which is going to be a row vector, X1, X2, X3. multiplied with 3, 2, 0, 2, 2, 1, 0, 1, 0, and this is symmetric. And then apply the x1, x2, x3 vector again. So let's see, we can go through this in whatever order we want. Because it's associative, so let's multiply it this way. I don't know. Let's do this one first. x1, x2, x3. So let's see. This is going to be the first. This is a 3 by 2 or 3 by 3 times a 3 by 1. So it's going to be a 3 by 1. And so that 3 by 1 is going to be 3x1 plus 2x2 plus 0. That's the first row. The second row would be 2x1 plus 2x2 plus 1 times x3, and then the last one would just be x2. And then when we do the second multiplication, we have a 1 by 3, a 1 by 3, and a 3 by 1, so it's going to be a 1 by 1, so that becomes a scalar. So this is going to be 3x1 squared plus 2 x1 times x2 plus x2, so that's 2x1 times x2, what? 2x2 squared plus 2x2 squared plus x2, x3, right? x2, x3. And then the last one is just x2, x3 again, right? Okay. Let's see. I think there are some like terms here. This is by itself. So that's 3x1 squared. Let's take a look at the other one. That's 2x2 squared. So those are the only terms that are squared. And then let's take a look at the ones that are not squared. X1, x2, x1, x2. So there's two of them. 2 times 2 plus 2 is 4. So that's 4 x1, x2. And then 2 x2, x3. So when I asked what you think of when you think of a quadratic, I was hoping somebody would say it's like a polynomial of degree 2. So this is like a polynomial of degree 2, except it has extra variables, x1, x2, and x3. So that's a quadratic form. All right, we probably should take a look at another example to see if we can make some observations. And the thing is that you can make any 2 by 2 or any symmetric matrix and then figure out what the quadratic form is. And so let's do another example. A is equal to, and let's do a 2 by 2 this time, make it a little bit easier for ourselves. Let's see, 3, -2, -2, and 4. All right, so let's try this one. Let's let the x vector equal to x1 and x2. And then so our q is going to be x1, x2, 3 minus 2 minus 2, 4, x1, x2. So let's see if we can quickly move through this. We have 3x1 minus 2x2 minus 2x1 plus 4x2. So we have a 1 by 2 times a 2 by 1. This is where we're going to get our 1 by 1, or scalar. It's going to be 3x1 squared minus 2x1 x2, and then minus 2x1 x2 plus 4x2 squared. I think if we simplify this, we got a couple of like terms that we can combine. 3x1 squared minus 4x1 x2 plus 4x2 squared. So I'd like for you to look at these two examples and see if you can kind of find a pattern. I'd sure hate to have to multiply things out if there's kind of like an easier way to find this. Yeah. Yeah, we could think about that. Each element kind of corresponds to their own column. So if we take a look at this one, this is probably a little bit easier to see because it's, first of all, it's a 2 by 2 matrix. Second of all, there's the zeros don't make things disappear. But if we take a look at this, the 3 and the 4, it's actually not a coincidence that it comes from this 3 and the 4 from the matrix. And then the negative 4 coefficient for this is what Byray was trying to say, that this is the 1, 2 position, the first row and second column position, and then this is the 2, 1 position. So this is the second row, first column position. And then if you imagine that's coming from x1, x2, and the order of x1 and x2 doesn't matter because you'll just be together. Then you see that negative 2 and negative 2 can be added together to be negative 4. So it actually is not a coincidence that it works out like that. That's exactly what happens. And so if we take a look at this, our 1, 1 position is 3. Our 2, 2 position is 2. And then we have a 0 times x3 squared here. And that's the third diagonal. And then now you have x1, x2. So the x1, x2, the 1, 2 position, and the 2, 1 position add up to that positive 4. And then the 2, 3 and the 3, 2 position, the 2, 3 and the 3, 2 position add up to this positive 2. And then had we had a 1, 3 position, we can see that in these places. Okay, yes. Oh, why are we doing this? We're doing this to try to identify a function, a scalar function, and try to identify a scalar function in quadratic form. And we're doing this because later on we're going to be interested in trying to figure out if what the quote sign, this is one application, is to try to figure out the sign of the quadratic form. And the sign of the quadratic form will tell us graphically, again, this is an application, graphically whether your quadratic form is positive or negative. And if we think back to calculus, there's this thing that we had in Calc 1 called the second derivative test, and in Calc 3, the test for concavity, sort of second derivative test in Calc 3. So this will give us some information about the second derivative test that we learned in Calculus 3, what that really means to be positive. So when a quadratic form is positive, we tend to say that it's concave up. And when it's concave up, then we can kind of see it's a local minimum. So that's one application of these quadratic forms. Well, the matrix that we're defining is here. So quadratic form is just anything that has a polynomial in more than one variable that has something to the second power. Not yet. Right, yeah, it's kind of like writing a matrix in polynomial form. That's one way to look at it. It's writing the matrix A in polynomial form, or writing a quadratic form into matrix form, which is what we're about to do. You know, we want to go from the matrix to a quadratic form, and then quadratic form into a matrix, and then we're going to mess around with that and try to find more information about it. If you want the star to be a matrix, I think the star of the show is quadratic form, and then the matrix is just the guy in the background that's, yeah. Yeah, we're just dealing with symmetric matrices. So let's take a look at finding matrices from quadratic forms. I have a whole bunch of problems here, but let's maybe it's easy enough to do. So instead of x1, x2, let's be flexible to say xy if we have to, or instead of x1, x2, x3 in 3 dimensions, let's be flexible to be able to say x, y, z. And so let's take a look at this first one. We have a quadratic form, and let's see if we can translate this into a matrix. So how does this look like in, what did they call it? Matrix of quadratic form. What's the matrix of quadratic form for this first one? Well, that was easy. 4, 0, 0, -3. Right? How about this one? So remember that this middle term, right? Kind of. Drop my pen, try to catch it, and then I poke myself. All right. And then how would we do this next one? 0, 1, 1, 0. Okay, piece of cake. I hope. What? Where did we get all this stuff from? So there's something interesting about A, our first example A. What can you say, first of all, what can you say about the matrix? More than that. it's a diagonal matrix, right? It's just a matrix of diagonals, zeros and everywhere else. So when you get a matrix that's just the diagonal, then you don't have this middle term. They call it the cross product term. I don't know if I like that term they use, but if they call it the cross product term, you can call it the middle term of the quadratic. But all it is something squared plus something squared, or plus and minus. And so I think it's easier to look at. Yes, I think so. Am I? Yeah, yeah. So that's an interesting concept. The idea that if we have a diagonal, then we don't have any cross product terms. Let's take a look at this next set in R3 now. So let's imagine that this is going to be a 3 by 3 matrix. Can you help me out here? X1 is X, X2 is Y, X3 is Z. Three to negative 3. I think if we get this last one, then we're all set. This is 0. And so this is symmetric, right? So this should be a negative 3. This should also be a 0. And then this last one is 5. So again, the diagonals here are the coefficients of the x squared, y squared, and z squared. And then all the other terms, this is x and the y. So this is the 1 spot and the 2 spot. So at the 1, 2 and the 2, 1 spot would be 4 split in half. And then here it's the 1 and 3 spot. So at the 1, 3 and the 3, 1 spot is negative 6 cut in half. So that's negative 3. And there's no yz term. And so the yz term would have been zeros in this case. Now, if I look at B, well, oh, I thought it was something different. Never mind. You guys got the picture, right? Let's do B real quick. What should this be? So 0, negative 1, 0 again. Would this be negative 1, 0, and so this is where the negative 2 goes? 0, negative 2, 4. Okay. All right, so we got a good idea to go from a quadratic form to a matrix and a matrix to a quadratic form. If you're having issues, you can just watch a video later on or ask the people who are yelling out the answers. They seem to know what they're talking about. Okay. Oh, yeah, so this is the definition of cross product terms, the non-squared terms of the cross product terms. So the question is, can we eliminate these cross product terms? So the cross product terms are these terms that are not squared. And then we saw in this example where Q is equal to 4x squared minus 3y squared, and then your matrix A is 4, 0, 0, negative 3. So this is an example with no cross product terms. Yeah, so this thing only has diagonals, which is going to play an important part for what we're doing. And so the question is there any way we can write our quadratic form with some sort of transformation so that we don't have any cross product terms because it's cross product. So yeah, so the thing to do is probably to diagonalize it. So that's going to be our next step, is to diagonalize our symmetric matrix A, which is what we did last time, didn't we? I forgot what we did last time. So let's go ahead and do that. So this is going to be a change in variable. We're going to change from variable x's to variable y's, which is why they prefer to use the x1, x2, x3, so that when they change variables, they call it y1, y2, y3. Yeah, we're going to diagonalize a quadratic form matrix, and then we'll see how the variable change happens that way. So the change of variable is going to be a transformation, essentially. We need to find a matrix to multiply x by so that we're going to get a new set of variables called y. And then that turns out that this special matrix that we're going to multiply x by is going to be an invertible matrix. And that special invertible matrix actually come from our diagonalization process. Did that make sense? I don't know. Can I? What did I say? We want to transform the variable from x to y. And so to do that, we're going to use a transformation matrix. And the transformation matrix P has to be invertible. So where are we going to find that matrix P? It turns out that we're going to find that matrix P by finding the diagonalization of A. So remember, when we diagonalize any matrix, we need to come up with this invertible matrix and multiply the matrix and then the inverse of the matrix on either side of the diagonal, and then that's how we diagonalize the matrix. So that's essentially, that's where P is coming from. So we want to transform this and get a Y matrix, or a Y, a set of new variables Y, so that P inverse times X is going to be that new Y, and then P is an invertible matrix. Maybe. All right, so here's the idea that I just kind of mentioned off the cuff. Let's see if these sentences would make what I say make a little bit more sense. So if you want to change that variable, we want to take a look at the quadratic form and see how that quadratic form is going to work. And so the quadratic form is A transpose times A, or X transpose times A times X. This is our definition of the quadratic form. So what we want to do is we want to change this X into a P times Y as per our transformation, just to get an idea where that P comes from. So if we change the x's with P times Y and P times Y, and then do some transpose algebra to that, and then do some regrouping, then we get Y of T times PTAP, which is very close to this idea of our diagonalization. So it turns out that if we can diagonalize A, yeah, yeah. So because A is a symmetric matrix, our P that we would be looking for will be orthogonal matrix, or we should say orthonormal matrix. And so that just can be replaced by D. And we know that if we multiply our variables by just the diagonal matrix, then this will have no cross product terms. Py where? Oh, because this is the replacement that we're going to try to do. So what the question was what uh, what is the matrix P to make this transformation from X to Y that we're looking for? And so this is how we're going to want to find P. We want to find P so that this is going to translate our X matrix to the Y matrix. And so that's X is equal to Py, and that's how we do that replacement. Yes. Well, no, it's our A transpose or X transpose AX quadratic form will become Y transpose DY, and which because our D is equal to this. But the fact that D is a diagonal matrix means that we're not going to have um, any more cross product terms. No, so it's just going to be something squared and something squared. Yes, those P matrices take care of that and make it into a diagonal. All right, so our task is to diagonalize a matrix, which is something that we are all experts in, kind of. So let's do an example. Oh, there's a solution here already. Yeah. Well, but y is also a column vector, and so p times the column vector is a 3 by 1. Three times 3 by 3 times a 3 by 1 is going to be a 3 by 1. So 3 by 1. Yeah. Otherwise, you can't do it, right? Yeah. Yes, because it's orthonormal, orthogonal matrix, and so P transpose is the inverse. And does it say that anywhere? Yeah. So the orthogonal matrix P would assume that P transpose is equal to P inverse, which means P times P transpose is I. Yes, we're going to find P because A is symmetric. If A is symmetric and then you find we can, I mean, it doesn't necessarily have that property, but the idea is that we can find it. If we don't get it right away, we're going to look for it. So the possibility that happens is that if the eigenvalues if one of the eigenvalue has multiplicity 2, then your eigenvectors are not necessarily orthogonal, and you just make them orthogonal. So P is what? Yes. Well, no, because you can switch the order of the columns. All right, let's see if we could do this example here. We have our star of the show, which is the quadratic form, and then the backup star is the matrix. So we can pull the matrix out easily, right? And this is a 2 by 2, so hopefully this would be easy enough to do. So let's do this example and see if we can change the variable of this quadratic form. And so our corresponding matrix is going to be what? So that's our matrix, and so our task is to find the eigenvalues and then all that the rest of the stuff, eigenvalues and eigenvectors. Should we do this by hand or should we call on our great Mathematica gods to help us? Do it by hand? You're just gonna waste time then. All right. So how do you find it again? I think it's a minus lambda I or something. All right. So we need to find the, what do you call that again? The characteristic polynomial. Oh man, this is hard. You know, since you're making me do this, I'm going to make you do this on the final, right? I'm just kidding. I was going to make you do it anyways. So this is a 2 by 2. So the determinant is pretty easy. It's 1 minus lambda squared minus 5 squared. Is that right? So 1 minus 2 lambda minus lambda squared minus 25. So whoops, this is a positive lambda squared. Lambda squared minus 2 lambda minus 24. So two things that multiply to 24 and add to negative 2. 6 and 4, negative. One of them's negative. So lambda minus 6, lambda plus 4. So we have our solutions. So we have our eigenvalues. So let's call one of them, let's call lambda 1 equal to 6 and lambda 2 equal to negative 4. Okay. Did we do that right? Yeah, when you do the matrix, you just have to make sure that if I call 6 lambda 1, then make sure the eigenvector for 6 is on the same column. Um, Later on, we'll see that it might be better if we choose the larger one to be our first one, and then in that order. That'll be useful for us in a couple of sections from now. So we have our e vector or e values. To find our e vectors, let's take them one by one. Lambda 1 is equal to 6. So we need to find the null space for 1 minus 6. I think that's negative 5. So the null space is going to be multiplied by negative 1, right? First column and add it to the second, and then you just have this, which means x1 is equal to x2. Are they equal or negative? So let's just call it 1, 1. And then lambda 2 is equal to negative 4. So this is 5, 5, 5, 5, 5, 5, 0, 0. Don't blink. X1 is equal to negative x2, so our v2 is going to be equal to one of them's negative, right? And yeah, I guess it doesn't matter which one's negative, but one of them is negative from the other. So this is nice. If you check it, if you dot it, it's orthogonal. That was one of the theories, is that if you find eigenvectors, then the eigenvectors from different eigenvalues will automatically be orthogonal. So the last thing we need to do before we get the matrix is to make them orthonormal. So just find the length and divide out by the length. So I would call this maybe u1 vector is the length is root 2. 1 over root 2, 1 over root 2. So this is negative 1 over root 2. 1 over root 2. So we have our P. Not only do we have our P, but we also have our D. So our D, if we're going to call this lambda 1 and lambda 2, so this is 6 and negative 4. Our P matrix has to correspond with a lambda 1 vector. So that's 1 over root 2, 1 over root 2, and then negative 1 over root 2, positive 1 over root 2. And so the inverse of P is just a transpose of P, which means your negative sign will just go on the other wing, the other side. We were looking for D, but now we can try to see what the relationship is. Yeah, yeah. Just for, it's all fun. Yeah. Yeah. Well, we can think about it that way, but we don't have to. Yeah. But yeah, if you think about it as a rotation, sine of pi over 4. No, you don't want to think about it as a rotation? Well, I wasn't going there, but now that you mention it, maybe we will. Let's take a look. We will. Calm down. So we have our P and our D. So if we change this into our new set of matrices, we have our Y. Our Q of Y would be, this is our diagonal, would be 6y1 squared minus 4y2 squared. And eigenvalues turn out to be square components. Almost like a spectrum. Kind of. Anyways, the relationship is that x is equal to p of y, or y is equal to the p inverse or p transpose of x. Which means if we put specific values for x and y, we can get specific values for, if we put specific values for x1 and x2, we can get specific values for y1 and y2. And then when we put it into this quadratic form, it'll be the same. Yeah. If all you want to do is write the change of bases without any cross product terms, then yeah, all you need is the eigenvalues. But if you want to know the relationship between x and y, then you need this p value, because this is the change. Yeah, so the formula starts off by saying your quadratic form x is equal to x transpose a x, and these are the x vectors, and then you change that to py transpose times a times py, and then this simplifies to y transpose d y, and your d is the diagonal, yeah, which is essentially the eigenvalues. Okay. All right. So let's got my grapher out. Let's take a look at how this thing looks like. And for us to kind of view this better, we need to define what this quadratic form should equal to, because a quadratic form by itself will end up looking like a piece of a surface. But It's better if we take a look at it in the context of something two-dimensional. So the quadratic form was, what is it, x squared, was it 10? Was it plus or minus 10? So if I were just to graph this, it'll graph a surface. But let's take a look at the surface being cut by some sort of a slider. And so depending on what the slider is, we'll have a different cut of the surface, which is going to be some sort of hyperbola. It looks like it's a hyperbola of some sort. Let's make this bigger. But notice the hyperbola, it's kind of slanted, right? It has a little bit of a tilt. And so what we'll do is we'll take a look at the graph of what was our form? 6 x squared minus 4y squared, and then we'll let it equal to a again, so that's the same a. So now we're looking at hyperbolas that are easier to manage. Actually, let's see. There's a way to. Yeah, as a matter of fact, there is some sort of rotation happening here. And the rotation is that 45-degree rotation that you're talking about. Yeah, well, that's one way to view this in this particular scenario. It's just a nice simple rotation. So let's take a look at our matrix A. How we're going to do this. Let's see. I'm going to rotate. And then I'm gonna take a look at the rotation as let's make it a little dramatic. Let's have it rotate kind of live. So the rotation matrix is cosine, negative sine, cosine. I hope. Pi over, what did you say? Pi over 4? Oh, this isn't done yet. There it goes. So if you look at just the right side, we're gonna do a rotation and we're gonna slowly change the angle of rotation until we get to pi over 4. No, it didn't work. Maybe this is negative. Is that going to work now? Okay, it looks like that'll work. So the idea is that we could take a look at this. This P happens to be for us happens to be a rotation matrix, which if we let our angles get closer and closer to 45 degrees, we're gonna eventually mimic that particular. Sure. Yeah. Yeah. So if you happen to be integrating over a I'm doing some sort of integral where your ellipse is tilted, or your hyperbola in this case is tilted, that's too hard to integrate. But if you do a change of variable so that it shifts over to a nice circle, maybe you can even make it into a circle by massaging it a little bit. Your original, your original graph is the red. As your original quadratic form is in red, and then your transformed quadratic form is on the right, which is in blue. With no yes, cross product terms. That's what they call it, and that has no cross product terms, which means it's a nice axis now. Our x and y axes are all nice and even. All right. Cool. So it turns out what we just did is based on this principal axis theorem. And the principal axis theorem tells us that there does exist this transformation. If you have an n by n matrix and there's an orthogonal change of variables, that's that p that we would find, that transforms a quadratic in x to a quadratic in y, and the quadratic in y has no cross product terms. And remember that it's based on looking for that diagonal matrix, and then the invertible p matrices on either side. If it's orthogonal, those matrices would be the actual transformation. So columns of P in the theorem are called the principal axes of the quadratic form. And then the vector y is in coordinate vector of x relative to the orthonormal basis. So the orthogonal orthonormal set of bases is a change of basis that we have. And so that does the change of basis. Yeah, what we're doing here changes the basis. So in fact, this is the relationship x is equal to p times y is our relationship, right? So if we take a look at the graph over here in y, we could take a look at the vector 1, 0, which is a basis in y. And we can run that through p. And if we run that through p, what's 1, 0 applied? So this is our matrix. Imagine p times 1, 0. What's p times 1, 0? Let's do this calculation over here. So p applied to the vector 1, 0. This is our e vector, right? This is a vector in y. This is our y vector. This is our p matrix. So apply 1, 0 here. What do we get? 1 over root 2 and 1 over root 2, right? 1 over root 2, 1 over root 2. So if we take a look at that in terms of this picture, and if we were to graph that vector, it what? Yeah. So 1 divided by square root, square root, square root, square root of 2, and then the same thing. So if we look at that, that vector is this vector over here, which is originally this vector over here that's been shifted. So if we take a look at that, the slider again to see how it shifts, this is originally where that vector is, right? And then as we turn it, it becomes the 1, 0 vector. So it becomes a nice basis vector for the y axis. Yeah. Yes, you're mapping, exactly. So you're mapping x into y. So the mapping, the p mapping goes from this graph to the right graph, left to the right, and then the p inverse goes from the right to the left. Okay. All right. Are you ready? already did that. Oh, there's the pictures. Example. Okay, so now let's get to classifying quadratic forms, because remember, we were interested in one of the motivations, at least, that I felt like was kind of important, is to figure out the sign, S-I-G-N, sign of a quadratic form, and that'll help us. That would help people in Calc 2. Calc 3. So with matrices, what we're going to be able to do is define the idea of positive and negative, but the word positive and negative is a little bit too superficial for a quadratic form when we're talking about matrices. So what we need to do is we need to kind of extend this, and then here are some definitions for what positives and negatives mean for matrices, or at least for quadratic forms, and we'll see how that translates to matrices. So quadratic form is positive definite if for all the values that you put into your x vector, or x1, x2, or x1, x2, x3, depending on what space you're in, that you're always going to get your quadratic to be positive. And then it's negative definite if it's negative, and if it's indefinite, it's neither positive nor negative if it assumes both negative and positive values. And then there's a couple more definitions that aren't really highlighted so much, and so I just kind of mention it here. The positive semi-definite means it could be equal to 0 if it wants to be, and then negative semi-definite is the same thing as negative definite, except it could possibly be equal to 0. So just on the general, just talking about this in general terms, we can think about these quadratic forms as paraboloids, where positive definite means it looks like it's going to be going upward. Also, think about it as concave up. Negative definite means it's going to be pointing downward. Again, thinking about it as concave down. And now indefinite, what picture, for those people who have had Calc 3, what picture should you think of when you think of indefinite, both positive and negative values? What? What? No, not quite. Close. What? No. Now, some of you guys were in my Calc 3 class. I was hoping, actually, anybody in my Calc 3 class? A what? Yes. A Pringle. You know what a saddle looks like? It's a saddle. What do you mean, what's that? Yeah, it's concave up on some parts and then concave down on other parts. So you guys know what a saddle is, right? You sit on the saddle. There's a part of the saddle that's a parabola going down. That's like the saddle that's on the horse side, and then there's another parabola that's going up, and that's where you sit on. It's going up on your front and your back side. And so here's a saddle. So think about a saddle as taking on positive and negative values around some small little intervals, small little neighborhood in your little space. So, all right. Let's take a look at this drawing and put it in our notes so you don't laugh at my drawing. I think it's good. That's the artistic part. All right, I can't move that around anymore. So anyways, The idea is that if we can identify these things as being positive, definite, negative, definite, and indefinite, then we're moving towards this idea of being able to classify a point, whether a point on a particular graph in Calc 3 would be concave up or concave down, or in this case, neither, and we would call that a saddle. All right, so let's see. Suppose the next thing to do is try to identify stuff. Oh, so here's the thing, and I won't talk much about the proof, but I'll include the proof in our notes, which is really just copied it from the book anyway, so you can just read it from the book. A matrix, if you have a symmetric matrix and then you have a quadratic form that comes from that matrix, then your quadratic form is going to be positive definite if all your eigenvalues are positive. So it really just depends on your eigenvalue. Negative definite if all your eigenvalues are negative, and indefinite if your eigenvalues are composed of both negative and positive eigenvalues. Yeah, yeah. So let's actually graph our example as a surface. And so our surface, what is it, was x squared plus 10 x times y plus y squared. And if we take a look at that graph, you see it looks like a saddle. Whoa. Let's try that again. So it is a saddle. and it follows with our conclusion from that theorem that says we have our eigenvalues. One was positive 6, the other one was negative 4, and so we would expect this to be an indefinite form. So here's some examples where they ask us to classify the quadratic forms. Let's do one that has 3. Oh, this one has 4. Oh, it says Mathematica. Should we brave it? Should we do it? Well, this problem number 4 from the exercise set is really the second derivative test from your Calc 3 class. Well, let's do one of these. Let's just copy all of them and figure out what to do. Let's not do the last one. So let's do problem number, I don't know. Let's do problem number 2 to check to see what kind of classify this quadratic form. So what this quadratic form might look like. So we have a negative x squared. So our matrix, original matrix A should equal to -1, -1, -1, and -1 again. Oh, wow. So let's find the eigenvalues. I know this is easy enough to do. Let's A minus lambda I is -1 minus lambda, -1, -1, -1 minus lambda. So that's -1 minus lambda squared minus negative is +1. So this is what is this? Lambda squared minus 2 lambda, right? And then there's a +1, and then there's a -1 outside, so that went away. So lambda and then lambda minus 2. So lambda is equal to 0, lambda is equal to 2. So the fact that there's a lambda is equal to 0 means it's probably going to be a one of those semis. And then this is a positive, so this is probably going to be semi-positive. Okay. What does that say? It says semi-positive. The graph look like? It would be, this is the q of x. So let's cross out the others. So this is your q of x. And then if you were to graph it, you could just graph it and see that it looks like it'll be kind of concave up-ish. Let's see if I can pull out, I don't know if I have Calc 3 notes here. When was the last time I taught Calc 3? It probably is a local minimum. Semi-part means there's like the whole axis that it might actually be equal to 0. Let's actually graph it. So z equals, oh crap. Yeah, kind of, maybe. So it's minus x squared. Oh crap, come on. Minus 2x times y minus y squared. So it's, wait, it's supposed to be positive. How come it's going down? Did we do something wrong? Ah, plus. That's a good thing we checked. So semi-negative, there's a whole row of zeros here that you're looking at. All right. So I was looking for the second derivative test. Let's see if I can find it in any of my old notes. Do I have lecture notes here? Notes, lecture notes. Oh, there's a shortcut. Oh, it's probably not going to happen. Oh, there it goes. What chapter was it? Second derivative test. Vector valued function. There we go. Functions of several variables. So this is a second derivative test as stated in a calculus class. And the second derivative test in calculus kind of invokes this idea of this fxx, fyy, fxy squared. And what happens is that this d actually comes from fxx, fxy, fyx, fyy. And what you would do, or what you can think about doing, is create a matrix of second order partial derivatives. And the matrix of second order partial derivatives would look like this. And then once you get that, create that second or matrix of second order partial derivatives, you define it as D. And then you actually, in Calc 3, they don't talk about this as a matrix, but really this comes from a matrix. And the matrix is, if you notice, fxx, fyy minus fxy quantity squared is really just the determinant of that matrix. So when the determinant is bigger than 0, then you have a chance for this being positive or negative. And then if it's less than 0, then it's indefinite, and so it's that other term. So the exercise that we're not going to be able to do from your book is this, number 24, and I just want you to look at the relationship between the fact about quadratic forms and the second derivative test, and there's really a tie-in over there. And if we had more time, I'd take a random function of multivariable some function of two variables, x and y, and then I would find the second derivative at a particular point, make up a matrix, and then figure out if that thing is concave up and concave down. And if I even had more time, we could do a quadratic approximation, a paraboloid approximation to a surface. You know, you talk about tangent planes, we can talk about tangent paraboloids in multidimensional space. And I'd rather be teaching Calc 3. All right, so that's it for now. See if you can make these connections between this and the other class, because it's fun.